In this video, I'm going to explain how to calculate the infiltration in buildings through windows and doors. Infiltration is the air that comes inside the building due to the pressure that the wind makes against the windows and doors. The windows and doors are usually installed inside the frame that has some gap between the door or window and the frame. As the wind pushes the door or window, the air finds its way inside the building through those gaps between the door or window and the frame. The amount of air that comes inside because of the wind pressure against the door or window is measured in CFM. These are cubic feet per minute. To calculate the CFM of air entering the building due to the infiltration, we're going to use an infiltration factor that depends on the window or door. For calculating the amount of air that enters the building through windows and doors, we will use these factors. We will use 0.37 per foot of sash crack for windows. We will use 0.5 CFM per square foot of door area for residential doors, and we will use 1 CFM per square foot of door area for non-residential doors. Notice that the infiltration rate for windows is measured per linear foot of sash crack, and the infiltration rate for both of the doors is measured depending on the door area in square feet. Let's look at an example here. Let's say we want to evaluate the sliding windows. If we want to calculate the sash crack for the sliding window, we're going to first assume that only the left side of this window moves right and left, and the right hand side of this window is fixed. It's attached to the frame. So if this sliding window measures 6 feet wide by 10 feet tall, then the sash crack is going to go around the perimeter of that section that moves and not the entire window. So that section will have 3 feet wide by 10 feet tall, approximately. So then the sash crack will be 3 feet on the bottom plus 3 feet on the top plus 10 feet on the left side plus 10 feet on the right side. So that means that the sash crack is going to be measuring 26 linear feet. Similarly, for a double hung window, what we're going to have is that now both sections move. The top section can go up and down, and the bottom section can go up and down independently. So if this window measures 5 feet wide by 10 feet tall, now the sash crack is going to be the top perimeter plus the bottom perimeter, right? We don't overlap the center. So this will be 5 feet plus 5 feet plus 5 feet on the horizontal side, and then 10 feet on each side of the window. So the sash crack is going to measure 5 plus 5 plus 5 plus 10 plus 10, which is then equal to 35 linear feet. Now let's see what happened with the single hung window. In this case, only the bottom portion of the window moves up and down. So if we have a window that measures the same size as the one before, where this is 5 feet and then this is 10 feet tall, we're only interested in the bottom perimeter, right? So this is the part that has a gap where the air can come in. So we have 5 plus 5 plus 5 plus 5. Now notice that this section is just half of the entire height. So if the entire height of the window is 10 feet, this bottom section is 5. So if we want to find out what is the sash crack, we can add 5 for the bottom plus 5 for the side plus 5 for the top plus 5 for the other side, and we get the sash crack perimeter to be 20 linear feet. For casement windows or basement windows, where the window opens around the entire perimeter, then the sash crack of the window is going to be the entire perimeter of that window. So if we have a casement window, for example, that measures 5 feet wide by 10 feet tall, then when we want to calculate the sash crack, we will calculate the entire perimeter. So for this particular door, we will have a sash crack of 5 for the bottom side plus 5 for the top portion of the window plus 10, which is going to be the side of the window, plus 10, which is the other side of the window, and that gives us a total length of 30 feet. Now that we have calculated the sash crack of each one of these windows, we can proceed to calculate how much air is coming inside the building through each one of the windows. For the first window, we have a infiltration rate of 0.37 multiplied by the length of the crack, which in this case is 26 linear feet. So we get a infiltration rate of 9.62 CFM, which is cubic feet per minute, and that is the infiltration rate through the sliding window that we calculated before. Similarly, for the double hung window, we're going to have an infiltration rate of 0.37 multiplied by the sash crack, which in this case is 35 feet, so we get 12.95 CFM. For the single hung window, we're going to get a 0.37 CFM per sash crack multiplied by the sash crack, which in this case is 20 feet, so we get as a result 7.4 CFM. Lastly, for the casement window that we had before, we get the infiltration rate of 0.37 multiplied by the length of the sash crack, which is 30 feet. So in this case, we will get 11.1 CFM. We saw how to calculate the infiltration for windows. So we have a 0.37 CFM per foot of sash crack, and we saw how to calculate the sash crack for different windows. In the case of doors, we have the infiltration rate is a little bit different, because now it's 0.5 CFM per square foot of door area, or 1 CFM per square foot of door area, depending if we're using residential or non-residential doors. So let's suppose that we have a door that is 3 feet by 7 feet. So the area of that door is going to be 3 times 7, which is 21 square feet. Now, the infiltration rate that we have is going to be 0.5 CFM per square foot of door area multiplied by 21 square feet that this door has, and that's going to be equal to 10.5 CFM. Considering that we're using the residential type of door, which has a 0.5 CFM per square foot of door area. If we're considering non-residential doors, now we have a 1 CFM times 21 square feet. That's going to give us now 21 CFM entering the building through that door that is now a non-residential. So for residential doors we have 0.5 CFM. For non-residential doors we have 1 CFM per square foot of door area. Please make sure that you notice that for windows the parameter is per foot of sash crack, so we will use the length of that sash crack. For doors it's per square foot of door area, so we use the door area. We already determined how to calculate the CFM. So to calculate the sensible load, we will multiply 1.1, which is a constant factor, times the CFM, which is the amount of air that comes through the windows and doors, times the temperature difference. Now this temperature difference depends on the conditions outside of the building and the conditions inside of the building. So for that we need to determine what is the design temperatures outside and the design temperature inside. The temperature difference that we talked about before depends between the outside and the inside conditions. The indoor design conditions are the conditions inside the building. So for winter we're going to assume 68 degrees temperature dry bulb, and for summer we're going to assume 78 degrees of temperature for dry bulb. The relative humidity for the winter time we will assume 30%, and for the summertime we will assume 50%. So that's going to allow us to calculate the amount of heat that the building needs to provide during winter time, or the amount of cooling that the system needs to provide during summertime due to changes in temperature of the air coming from the outside to the inside. For the conditions outside of the building, we will depend on the location. So in our case, we are in Miami, Florida, and when we're dealing with heating, the dry bulb or outside dry bulb is going to be 46 degrees Fahrenheit. For cooling, which is used during summertime, we're going to assume that the temperature outside is 91 degrees Fahrenheit. So the temperature difference that we're going to use in this case will depend on the time of the year. For winter conditions, we are going to use a temperature difference of 68 minus 46, which is going to be equal to 22 degrees Fahrenheit. For the summer, we're going to use a temperature difference of 91, which is the temperature outside in Miami, minus 78, which is the temperature that we're setting for the comfort zone inside the room, and that's going to be equal to 13 degrees Fahrenheit. So that's going to be the assumptions that we will do to calculate the sensible load due to infiltration when we know the CFM, because we calculated using the sash crack, and the temperature difference will be one of these two that we have, depending if we're in winter conditions or summer conditions. The humidity ratio depends on the conditions of the dry bulb and the wet bulb or relative humidity. So during summer, we are going to assume that the humidity ratio difference is going to be 38 minus 30, which is equal to 8. During the winter time, we're going to assume that the conditions for the humidity ratio are going to be 138 minus 70, which is equal to 68. These determinations depend on the conditions for the outside and the inside of the building. The previous conditions that I explained for the humidity ratio, remember the humidity ratio is calculated on this scale here, depends on the dry bulb, which is measured here, and in sometimes the wet bulb, which is across this line, or the relative humidity, which are the lines that comes in these directions. So depending of the conditions of the outside for different cities, or the conditions inside for the comfort zone, then the humidity ratio is just directly read from the psychrometric chart. I hope that you find this video useful and that you now understand how to calculate infiltration for your course project.